Okay, thank you. Let's continue. So I hope you all remember we were looking at this discrete Schrödinger equation. We found out how to derive some dispersive estimates for this, and we also have seen how to get further estimates, these Richards estimates, out of the basic ones. And in the last part I promised you to talk a little bit about some applications to nonlinear equations, in particular here this discrete nonlinear Schrödinger equation. And I'm going to present some very basic tools from nonlinear functional analysis in order to solve the Cauchy problem, and also in order to show some existence of some non-trivial solutions. Okay, so the first thing I'm going to recall is, oops, wrong direction, differentiation in Banach spaces. Okay, so the good news is that more or less everything you know from your analysis course and from differentiation in Rn, almost everything carries over to the Banach space setting with almost no changes. So most of the basic results just go directly through without modifications to the proof, and hence I'm just going to recall a few things, and I'm not going to give you detailed proofs, but just take any textbook you want on the finite dimensional case and then read the proof and check that it makes no difference whether you have Rn or a Banach space. Okay, so I'm assuming I have two Banach spaces, X and Y. Everything is going to happen on some open subset U. I'm going to assume that the first Banach space X is real. I'm emphasizing this because most of us do spectral theory. We are used to having complex valued Banach spaces, but be aware, if you define differentiation in a complex valued setting, then of course you have complex differentiation, which is a much, much stronger concept. Okay, so for this reason, the values of the function could be complex, but the range here we want to be, the domain here we want to be in a real setting. Now, definition, just as what you would do in Rn, you say that the function is differentiable at the point if you can approximate it sufficiently well by a linear function. So we start at some point x, we go a little bit into the direction of u, and then we can write this as the point f of x where we have started, plus some linear transform applied to this direction, plus some lower order terms. So this little o here is just the usual Landau symbol. I presume you know this, because this is the common notation. But I guess you want to say that the Arnold principle applies here, or would you? That's strange, because to me this notation is totally... Is this a European thing? Okay, I never... Okay. Yeah, so for me it's the most common notation. So the name for the notation. So I wasn't... I don't know. I mean, I just copied this from the textbooks which I used to use. Yeah, many German textbooks, but I also think English. Yeah, I presume if you go to Wikipedia and look up Landau symbol, this is what you will get. So I would consider this notation standard. But anyway, we all know what we are talking about. You have... No, you can get away with less, but then things get really tricky. Okay, so there's something which is called convenient vector spaces, but I don't want to go into this direction. So you need some special locally convex spaces where you can define differentiation in a good way. But for us and for most applications to PDE and so on, the Banach space valued setting is good enough. But this is not the best you can do. But if you want to do better, you really need to work much, much harder. Okay, let me just put it like this. Okay, and of course also let me emphasize that this here is a linear operator, and by linear operator I really mean a bounded linear operator. So this also needs to be emphasized. So at this point, no domains here, nice bounded function. Okay, And it's usually called the Fréchet derivative, even though since we will be mainly dealing only with this, I'm going to drop the name Fréchet pretty soon and just speak about the derivative, and I will mean precisely this one here. Of course, the derivative itself depends on the point where it was taken. We have here again a Banach space, and of course we can ask ourselves, is it continuous? And if yes, we will just write C1 as usual. So this is just the standard notation, nothing fancy here. Let me just make two remarks. First remark is that you should think about this, that this derivative is really well defined. So there is only one derivative. The important thing is that U is open. You need to be able to approach from all directions. If you don't have sufficiently many directions, it's no longer unique. Okay, and the second thing about the complex thing I already mentioned, so I don't need to say anything here. I also only very briefly mentioned that there's a weaker concept, the Gateau derivative here. So you just look at these directional derivatives. So you take one fixed vector, scale it, and then define a derivative as a limit as in the usual way. But this is a directional derivative, and it's a really weaker version here. Even if this exists everywhere, it doesn't have to be a linear operator. For example, it could also be an unbounded operator, and also be aware there's nothing infinite dimensional here. That already is true in finite dimensions. Okay, so you can write down an example in R2 where this limit exists everywhere but is not a linear function. Okay, but we will look at the Fréchet derivative and just speak about the derivative, and then should be good enough. Okay, so now here is the good news. Almost everything stays the same. Of course, it's defined as limits. It's linear. If you're differentiable at a point, you are continuous. If you split your domain, if it's a product space, so in some sense you have several components, it suffices to look at the components. So the derivative is just given by the derivatives of the individual components. If all of them are C1, then the whole thing will be C1. Same thing if you split the domain. So if you split X into a product of finitely many Banach spaces, you can look at partial derivatives. So you just keep all the others fixed, take your derivative with respect to this one. And again, you have the same result. So you have this kind of gradient-like formula. Right here, you can build up the full derivative as a sum of the individual pieces. And if all of them are continuous, then the whole result will be C1. You have the chain rule. You have this multidimensional version of the mean value theorem. So nothing much changes, and also the proofs don't change. So you don't have to work hard. You just copy the old proof. Okay, so let me give you two examples and show you how to compute these derivatives. And I'm doing this for two reasons. The first reason is that you see in some situations, and this is why I call this the good guy here, if we look at these LP spaces, at these discrete spaces, then usually the situation is quite nice. Afterwards, we will look at the big LP spaces, and we will see that there things can go wrong. And this in some sense is the reason why PDEs are much, much harder than these difference kind equations. Like the discrete settings, you need to find the correct space, you need to find the correct formulation in order to make things work. Okay, so what am I doing here? I'm just taking a normal C1 function on R. Think about f of x is equal to x squared or something like that, a polynomial, whatever you want. The only restriction, I want it to be 0 at 0. You will see why in a second. And I take the corresponding operator, which I get by just applying this function to my sequence entry-wise, and hence I get a new sequence. And I can ask myself, is this a nice operator? Can I differentiate it? Is it C1, as you might hope if you start with a C1 function? Okay, and I'm claiming, yes, this is true. The Fréchet derivative is nothing else than the multiplication operator with this derivative function right here applied to the sequence xn. Okay, so let's think about for a second why this is true. first observation is we start at 0. We can use the mean value theorem to go away from 0 and estimate this like this. Of course, we will not have a global estimate, but as long as we stay on a finite ball of radius r, there will be some corresponding constant such that we can estimate it like this. Of course, here we have to be careful. Here we're using really that things is in a finite dimensional setting, that r is one-dimensional setting, because we are using the fact that the derivative is continuous and hence takes a maximum on a fixed ball of radius r. Okay, that's not true in infinite dimensional setting. Please recall, of course, the unit ball in the Banach space is compact if and only if the space is finite dimensional. Okay, but this is definitely true, and that means we can easily estimate the result of our operation in LP by just taking this constant where we choose the ball sufficiently large to have the maximum of this sequence here. Please recall, if you have a summable sequence, it must be bounded. And moreover, of course, the maximum must be smaller than the sum over the absolute values of all entries here. Okay, so let's see, we see this is a nice operator from LP to LP, and even it's locally Lipschitz, and this argument also shows that f prime is a bounded linear map, so we just need to verify that it is indeed the derivative of our function. That's also not very difficult. Of course, what you do is you write down Taylor's theorem with reminder, so you write it like this. You use the fact that your derivative is uniformly continuous, at least on a compact set. Again, choose some suitable radius as before. Then you have uniform continuity, so that means for given epsilon, you can find a delta and some r, such that when these two sequences satisfy these estimates here, you have this estimate on the other side. So just plug this in, and then this gives us precisely this required estimate here for the derivative, and shows that your function is indeed Fréchet differentiable, and what I have written down before is precisely the Fréchet derivative. And extending the argument a little bit, you can even see that this function, that the derivative is continuous, and you are C1. Okay, so nothing fancy happens here. Everything works very nice, but still you need to work a little bit. Okay, so you really need to give a careful proof for these kind of things, because otherwise things can go wrong. And this is the content of the second example, which I've called the bad guy here. Now we make the very same thing as before, but we take L2 on a finite interval, 0, 1. You can take LP and so on. I'll just take this case for simplicity. Again, I'm taking a function. Now I'm even more explicit. I'm taking the sine function. Okay, this is globally Lipschitz continuous, as smooth as you want, so it hardly will get any better. Okay, so we have this Lipschitz estimate here, and of course this Lipschitz estimate, as before, tells us that if we insert a square integrable function, the result will again be square integrable, so it's well defined. And moreover, we even get a corresponding Lipschitz estimate for this operator here. So this operator is Lipschitz continuous with constant 1. Okay, so far everything is as one would expect. Everything is very nice. You can also check, we will do this on the next slide. It's Gateau differentiable, and the Gateau derivative at 0 is just the identity, but it turns out it's not differentiable in our stronger sense, in the Fréchet sense. So be careful, even in simple situations, things might go wrong. Okay, so let's start with computing the Gateau derivative. Of course, we have this basic this basic limit right here. Just use, how is it called? De L'Hopital. Just use De L'Hopital. Then you get this pointwise for fixed t. Okay, t is my index for the function right here. But once you have it pointwise, you just need to observe that you have this bound right here. So dominated convergence tells you that the same limit holds in L2. So that means the directional derivatives are okay, and you just get the identity as your differential. Now, what goes wrong if you look at Fréchet derivative? Well, look at this very simple function here. This function is just pi up from 0, starting from 0 up to 1 over n. So I'm just shrinking this function that obviously goes to 0. I mean, you can compute the norm. You see it goes to 0 like 1 over square root of n. But if I try to plug this in the definition, and if the derivative exists, of course, it must be equal to the Frechet derivative. So this here would need to go to 0. But now the problem is that the sign, and this is why I've chosen p here, kills this function. Okay, it's gone. So this here is not there. So this is equal to 1. It does not converge to 0. And it's not differentiable, even though your function is as nice as it gets. So be careful. Things can go wrong, and in particular with LP spaces, things will go wrong. By the way, the problem here is that the functions in this space are discontinuous. If you would replace the situation by some continuous functions, you can take continuous functions with maximum norm, or also some Sobolev spaces, H1, then this is no longer going to happen and things will be fine. Just to emphasize again, when you do PDE, it's important to have the right spaces, then things will work, otherwise they might go wrong. Okay, so far everything is good. We can continue defining higher derivatives in the usual way. Our function f has a derivative. This function is again a function which now doesn't have values in y, but has values in this Banach space of bounded functions. So we can go on, compute the second derivative, and say it's differentiable and so on as before. If the second derivative is again continuous, we say it's C2 and so on and so on. And of course you can go on to higher derivative if you want. You just have to be aware, of course, what you're getting here. We started with a function with values in y. The first derivative will have values in the linear operators. The second derivative will have kind of two arguments, and it will be bilinear. So it will be a bilinear function, and higher derivatives then will be multilinear functions. By the way, you can of course also show that it will be symmetric, at least in the C2 case. This bilinear function will be symmetric. Okay. And you can go on like this, defining derivatives of arbitrary order. I just revisit my good guy for a second, and you can do it yourself. It's a nice exercise. Compute the second derivative. You will just see, okay, it's this multiplication operator with the second derivative of the function and apply it to these two vectors here. So this is the bilinear function you get out of this. So no surprises here, no miracle. Everything works nicely. Now I'm coming to some little bit more non-trivial stuff, and the first thing I want to mention is the implicit function theorem. Of course, you could also on the slide before go on and prove Taylor theorem and so on. All that exists. I'm not going to need it. What I'm going to need is the implicit function theorem. This is going to play a crucial role, and hence I'm mentioning here. Don't worry about all the formulation you see here. It's just precisely the same result as you have in finite dimension. You have a function f. It depends kind of on two variables, one living in x, the other one living in y. Everything, of course, is local, so it doesn't have to be defined on the entire space, just on some open subsets. Takes values in another Banach space Z, and if you assume that this partial derivative with respect to the first variable exists and is a nice bounded operator, which is an isomorphism, so we can invert. So that means it's invertible, and the inverse is a bounded function, so bijective, and the inverse is continuous. Of course, the continuity you get from the open mapping theorem. That doesn't need to be checked. Then you can locally solve this equation here for the first variable in terms of the second one, and moreover you also have uniqueness, so there's a unique solution given by this local solution right here. And you also can write down using implicit differentiation, using the chain rule, basically a nice expression for your derivative right here. And I'm not giving you the proof, but I'm just reassuring you it's the same as in the finite dimensional case. Banach fixed point theorem, that's of course already in a Banach space, so nothing has to be generalized here. And then you just write this as a fixed point equation, verify the assumptions of the Banach fixed point theorem, and then that's it. In order to get the differentiability assumptions Here you need a little bit more, you need this uniform contraction principle. But it's the same, so it's no difficult proof, it's very rather short, and it's the same as in the finite dimensional case. Okay, once you have the implicit function theorem, you can prove local existence for ordinary differential equations. And moreover, that's maybe quite nice because it's not so well known. You can use the implicit function theorem to get this fully fledged version here. So I'm looking at a vector field. The vector field f can depend on t, on x of course, and also on some parameter lambdas if you want to. I'm not going to need this, but I'm just mentioning that it's possible, and you assume that your vector field is CR, has R derivatives, then locally you have a solution which is also CR with respect to everything, also with respect to initial time, initial condition, and also with respect to these parameters. So really the full-fledged version, and the nice thing is you get this with very little effort out of the implicit function theorem. Maybe from your ODE course you know usually one does Picard-Lindelöf, but then you need to work much harder in order to get differentiability. Okay? But anyway, whatever you do, it will give you a local existence result. So also local existence of ordinary differential equations in such a Banach-valued space settings is no problem and works as in the final dimensional case. Of course, once you have local existence, you will also worry about global existence. Is there a global solution? And there is also a similar criteria for global existence. So if you suppose that the vector field, now I have dropped the dependence on parameters, that the vector field is bounded along your trajectory on finite intervals, then you indeed have a global solution. So if the solution is not global, the value of the vector field along the solution must blow up. And maybe let me emphasize here, in the usual ODE case in Rn, you might find different formulations. In particular, you might most likely find the formulation that the solution itself does not blow up. And here you have to be a little bit careful, because bounded sets are not compact. There are some differences here in the infinite dimensional setting, and this is the reason why I'm writing f here and not x. Okay? In most cases, f being a continuous function will map bounded sets to bounded sets, but this is not necessarily true. Okay, some things here can go wrong. You have to be more careful about these kind of things in infinite dimensional settings. For a linear function, it's not going to happen. We know a linear function, linear operator is continuous if and only if it maps bounded sets to bounded sets. But without linearity, that might no longer be true. Okay, so a little bit tricky. Most functions, and in particular the functions we're going to deal with have this property, but you can write down some examples where these things go wrong. Okay, so we even have a criteria for global existence, and now we have everything together, and we can try to apply this to the discrete nonlinear Schrödinger equation. I have written it down here again, and the claim is it has a unique global non-preserving solution, and the Cauchy problem is well posed in the sense that the solution depends continuously on the initial condition. For me, it's sufficient to have this result. Of course, the point is, as you see, you need to look at this function right here. As it stands, it's u times absolute value of u to the power 2p. It will be C1 as soon as p is positive. And p is equal to 0. That's just a linear piece. I can add it to the linear operator, so this case is not interesting. Anyway, you will not have more than C1 unless you assume a higher power here because of the absolute value, right? But you could formulate the result something like, if p is sufficiently large, then you get CR with R depending on p, but I don't want to go into this. And also the dependence on the initial condition will be C1, so not only continuous, but C1 as we have seen before. Okay, maybe also emphasize that if something is unclear, then please interrupt me, because I realize I'm already going very fast. So if I'm too fast, the best way to slow me down is to just ask some question. Okay, and there is nothing we have to do in order to prove this theorem. First thing is, as I mentioned before, it's a C1 vector field. Why? Because this is linear. Linear functions are smooth. They are C infinity. The first derivative is the linear operator itself. Since it doesn't depend on x, every higher derivatives will vanish. So this is C infinity. And this here is of this type f of u, as I have discussed before. And it will be C1 if the corresponding function on the real line will be C1. Okay? So that's very simple. We see that this is C1, and hence we get the local result out of the local ODE result I have presented you before. In order to get global existence, we need to show that things don't blow up. Now you need to do a little calculation, write down the the L2 norm, and differentiate this, and you will see that it will vanish. So you will see that this thing here preserves the L2 norm as long as it exists, and in particular the L2 norm cannot blow up. And also you immediately get from the structure we had before that the L2 norm of the vector field cannot blow up in this situation, because this here is linear, maps bounded sets to bounded sets, and we also had this Lipschitz estimate before, which shows us that this function here maps bounded sets to bounded sets, so no problems here, and we get that the norm is preserved and cannot blow up, and we have proven this theorem with almost no effort. Of course, let me emphasize again, if you want to do the same thing in the continuous case for the continuous one-dimensional nonlinear Schrödinger equation, then you really have to work harder. It's not going to work so easy. Why? Because then your operator h here is not going to be a bounded operator, it's going to be an unbounded operator. So you have to work with the semigroup theory I have mentioned before. You still can use some of the ideas here, but you need to find the right spaces, you need all kind of estimates, and in particular you will need the Strichertz estimates in order to prove local and global existence of solutions. And also in the continuous case, things will depend on the sign here, whether you have blow up or not, because you need more control on the solution. Just being able to control the L2 norm of the solution is not good enough. You also need to control the derivatives. And for this, you can use that. Here I've just shown you the L2 norm as a conserved quantity. There are more conserved quantities, but they have this sign, and then it depends on the sign whether this gives you good estimates on your solution or not. So for one sign, things are fine. For the other sign, things go bad. Okay, I also briefly mention you could replace L2 by some other spaces. You could replace this by some weighted spaces, and you will more or less get the same result. Of course, then you do no longer have conservation of the corresponding norm, but things don't go bad too wrong. For example, I mentioned something here. If you look at exponential weights, you still get a nice expression, and you can use Grunwald estimates to show that it remains bounded so it doesn't blow up. So you could also investigate this in different norms, and hence drawing conclusions like if you have a certain decay of your initial condition, then this decay remains preserved by the time evolution. Okay, all this can be done, and maybe that's also one interesting thing I'm mentioning here, that if you take weights, they can be at most exponential. Why can it be at most exponential? I mean, there are still Banach spaces if I take a weight like e to the x squared. Powers will work, everything which is at most exponential will work. If it's super exponential, it will not work. It's one of the things where you have to be careful about verifying your assumptions. And what you need to verify is, for example, I'm always going in the wrong direction. Is this a bounded operator? Okay, how is this operator composed? It's shift in both directions plus the bounded potential. The bounded potential, the weighted estimate is not going to care about. But what about the shift operators? if you shift by one place, the norm depends on the ratio of the two weights at the original point and the shifted point. That must be bounded, which is the same as saying the weight must be at most exponential. Okay, always be careful in the infinite dimensional setting about really verifying everything and not just saying, okay, that's a linear operator. It's clear. You need to verify that this is a bounded operator. And for example, if you do this in a weighted space, as soon as your weight is more than exponential, shift operators will no longer be bounded operators. So really pay attention to the details. This is what I would like to say here. Otherwise, things can go wrong. Okay. So we have existence, we have solved the Cauchy problem, so let's try to go one step further. One is interested in solutions of this equation, and in particular one is interested in solutions of this type right here. So some stationary solution of the nonlinear discrete Schrödinger equation. You have this e to the it omega times some stationary profile phi of n. If you plug this ansatz into the equation, then you get the corresponding stationary equation, and one asks oneself, are there any solutions? Of course, there's the trivial solution, that's clear, we're always going to have this, but are there any non-trivial solutions to this equation? How can we answer this? Well, the answer is, again, we use nonlinear functional analysis. So we just say, okay, this is a function in a Banach space, and we look at zeros for this function. We know one zero, we know the trivial zero, and if there should be another one, then that means that somehow must branch off from this trivial solution. So that means that locally the zero set of this function here must change. Okay, we have a nice C1 function, and locally the zero set is not going to change if the corresponding derivatives are not vanishing. Okay, because then the implicit function theorem tells us in a neighborhood we can solve, and there is precisely the solution we already had, and there cannot be another one. Okay, so this is the standard observation in bifurcation theory, that the implicit function theorem tells you that the corresponding derivative must vanish for something interesting to going on. Okay, so these are the points you need to search for. Once you have them, of course, it's still not clear that something interesting is going on there, because it's just a necessary condition that the implicit function theorem fails. But if it fails, the question is, can you show that there's a real reason, that there's a real change? Okay, so this is the next thing I would like to discuss. So our approach is the following. We look at this equation here in a Banach space. So this is a function in the Banach space R plus little L2. Omega here is considered to be as a parameter, so this is real valued, and this profile here will be in L2. Okay, and this is the equation. I've just copied it from the previous slide, and we have this trivial solution. So if phi is 0, everything vanishes, everything is okay. When do we have non-trivial solutions? Well, the implicit function theorem tells us when we differentiate this function with respect to phi, so we take the Fréchet derivative, if this is not vanishing, then locally we can solve. There cannot be anything else beyond the solution we already have, beyond the trivial one. But if it's not invertible, then something might go on, so we should look at these points. Okay, what is the Fréchet derivative at the trivial solution? Of course, we have the linear part right here, plus we have the derivative of the nonlinear part, but the nonlinear part is just this function here, and this derivative vanishes at 0. So hence you don't see it, and you just have this simple linear equation right here. Well, we are asking about non-invertibility of this operator. This is just our Jacobi operator. So if this has an eigenvalue, then something interesting might go on. Okay? So the point is, interesting things can only go on at the eigenvalues of our linear Schrödinger operator. And again, you see this principle. You look at the nonlinear equation, and in the end it boils down to solving a linear problem. Okay? Because this must not be invertible. Okay, of course we have to be, that's true. We are in an infinite dimensional setting. many things can go wrong. So either it could be not injective or not surjective, but not surjective, I'm not going to look at this. Okay, one would not expect something interesting happening because of this, but in principle you're right. If this operator has no kernel but is just not surjective, then also we cannot apply the implicit function theorem, at least not the version we have seen before, and something could go wrong. But I'm just looking at the case where it's not invertible. So this is the assumption I'm making. I'm going to look at an eigenvalue and I'm trying to find out what is going on at this eigenvalue. Okay, so this is, you're true, it's not really a fully mathematical statement, but at a non-trivial, at an eigenvalue, then it's possible that the non-trivial solution branches off from the trivial one. And important thing is, of course, this is just a necessary condition. So for the sufficient condition, we will need to work much, much harder. But of course, this is our aim, to get a sufficient condition on this. Okay, so the procedure is a two-step procedure, what we're going to do. The problem is, because of this trivial solution, we don't see anything in some sense, right? This is here, so we cannot apply implicit function theorem, so somehow we need to split this off. That's the one thing. And the second thing is, we still would like to reduce everything to a simpler situation which is familiar to us. We would like to reduce everything to a finite dimensional situation. So the first thing is we reduce it to a finite dimensional situation. This is this Lyapunov-Schmidt reduction, and once we have this, we split off the trivial solution, and then after splitting it off, again apply the implicit function theorem, and this will give us the desired result. Okay, so we are going one step back, and we won't need the special structure of the problem before. So far everything will be quite general. So we have a function depending on omega and x. So omega will be a real number and x will be in our Banach space. We are assuming that the situation is C1, that this function is C1, and we assume that we have this trivial solution. Okay, so that fits what we had before. More we are not going to need at the moment. So first thing is, we would like to effectively reduce this to a finite dimensional problem. Okay, so we have seen interesting things are going on if the Fréchet derivative here is not invertible. So we will assume that we will have a kernel. We don't want things to go too bad, so we assume that this kernel is finite dimensional. We also will assume that on the other side, on the range side, not too many things go wrong, so that on the range side there's also a finite dimensional space missing. This is saying that the co-kernel is finite, and we're also assuming, we will see why in a second, that the range is closed, even though we have already discussed this. The third condition will follow from the first two conditions, so you get this for free. Okay, anyway, and this is what we have called a Fredholm operator. So there's a well-developed theory for such situations, even though at this point we are not really going to need this. We are only going to need a very tiny thing, and this we will see in a moment. Okay, so why are we doing this? We are doing this for the following reason, because we want to split our space. We want to split the range into the kernel plus the rest, and we also want to split the domain into the kernel and the rest, and also we want to split the image side into the range and the rest. Okay? We have assumed that these spaces are finite dimensional and that this space is also finite dimensional, that this range is closed, and hence this can be done in a nice way. Okay, so that means there are continuous projections going from x to the kernel, and also a continuous projection going from, oops, there should be y here. No, x is equal to y in my situation, which is also going on the range side from x1 plus range just to x1. This is what is missing in the range. Okay? x1 is finite dimensional and the kernel is finite dimensional. So these are projections onto finite dimensional spaces. And here I don't want to say too much about it, but these assumptions here ensure that you have existence of these continuous projections. Okay, so if you have a subspace in a Banach space and you would like to complement this in such a sense that you write this as a direct sum with your space plus another space, then this is only going to work nice in certain situations. This is the complemented subspace problem in Banach spaces. It's very deep, puzzled mathematicians for quite some time, cannot always be solved, but if you assume that your spaces are finite dimensional, then it works. Okay? And closeness is always important in order to get these continuous projections right here. So in some sense, this Fredholm assumption here really is equivalent to saying I can make this splitting of my spaces into the finite dimensional piece plus the rest in such a way that I have a nice continuous projection. Okay? This is really what this assumption here ensures. This is what I'm using here. Okay, and moreover, let me emphasize again what the important features here are, and let me also emphasize how you should think about this Fredholm operator in the first place. Okay, we have assumed the one space, the kernel, is finite dimensional. We also have assumed that the other space, this x1, is finite dimensional because that's basically your co-range here. And with respect to the splitting of the space, we get a block structure for our operator. And this just looks like this here, okay? This is from the kernel to the kernel and so on and so on. This is the only piece where something interesting is going on. Everything else is zero. And this interesting piece here is more or less restricting your operator A to x0, which means factoring out the kernel. So this thing will be injective. And then also restricting on the range side to the range so that you get something surjective. Okay? So this here, the interesting piece is now a bijective operator. Again, we are using open graph, open mapping theorem, which tells us that this here has a bounded inverse. Okay? And this is really how you should think about a Fredholm operator in the first place. You can split your space by splitting the one side into kernel plus the rest, finite dimensional plus an infinite dimensional rest, and also split your image side into your range, which is infinite dimensional plus a finite dimensional rest, and then think of your operator as such a block operator where this only non-trivial block is invertible. So it's a nice bounded and bounded invertible operator. This is how you should think about this situation, and as emphasized before, it's precisely this Fredholm assumption which makes this work. Okay? Okay, so now the procedure is clear. We want to solve this system right here and think of this as an infinite dimensional set of equations. Okay, so if we think in terms of coordinates, that means there are some finite number of coordinates depending, corresponding to the kernel. They need to vanish, and then also the remaining coordinates need to vanish. So of course I can say this will be 0 if and only if the first components here corresponding to the kernel vanish and the remaining components vanish as well. Moreover, what I plug into this equation, I can also split it accordingly by saying this x I plug in, I write it as some finite dimensional vector which lies in the kernel plus the rest, which is then of course necessarily infinite dimensional. So I can split this thing right here in this way using my projections. So I'm splitting x into the kernel piece plus the rest, and I'm splitting this function f into the projection onto the finite dimensional part which is missing from my range and the range. Okay? This is just a reformulation, nothing happened here. Of course, these are bounded linear operators. They have as many derivatives as I want. So the function will be as smooth as what I have started with. I have started with C1. So again, this thing will be C1. Moreover, according to this splitting, the partial derivatives are just the blocks in my operator before. Partial derivatives, of course, at the bifurcation point, at my eigenvalue and at the trivial solution. Right here, so these are just these blocks. It's just splitting everything according to this block structure. Okay, and you can see it already here. This now is invertible. So for this piece, we can apply the inverse function theorem. and this is of course precisely what we're going to do. We are going to apply the inverse function theorem and locally solve the F2 component. And please remember, the F2 component is the infinite dimensional one. The F1 is the finite dimensional one. This we can solve, of course not explicitly, but in theory, the implicit function theorem tells us we can solve this. There's some function psi, which is C1, exists in a neighborhood, and if we plug this into the second equation, then the second equation will be fulfilled. Okay? And of course now we can take this function right here and also plug it into the first equation. The first equation will not be fulfilled. Okay, you have to be careful here. This is really is equal this to 0, and this should be read should be equal to 0. This is the equation we want to solve. Okay, let me just emphasize this. So this we have coped with. It's done. We can forget about it. This is what still needs to be solved. But this now is finite dimensional because U is finite dimensional and the range here is also finite dimensional. So that means we have effectively reduced our infinite dimensional problem to a finite dimensional one by applying the implicit function theorem. And this is this Lyapunov-Schmidt reduction for this particular problem which we have done right here. And of course, you can work out the derivatives, so just tracing all the definitions back using the implicit function theorem tells you that this derivative is given by this here. It vanishes because we have seen from the block structures before, this was just this block right here, vanishes, and also you can compute the derivatives here and you get this problem right here. So it preserves these features. Of course, the whole procedure preserves the trivial solution. So this F tilde, this one finite dimensional thing now still has the trivial solution and it still satisfies this bifurcation condition. Okay, that something interesting is going on here, that this derivative vanishes. Okay, so once we have done this, now we can try to look at this finite dimensional system and ensure that there is something non-trivial going on, and this typically goes under the name Grandal-Rabinowitz theorem. So this is the next step we want to do. We have reduced it to a finite dimensional system. Now we want to investigate this and find some condition such that we really get a non-trivial solution for this finite dimensional system. Well, now I would like to simplify the situation a little bit. That's not strictly necessary, but it will be sufficient for us, and we want to have something which can be easily understood. Once you have understood it, it's clear how to generalize the whole thing. So we're going to assume that the kernel is one-dimensional. So finite dimensional to one-dimensional, which basically boils down in our application to requiring that this eigenvalue is simple. Okay? So we assume we have a simple eigenvalue for our system. Moreover, I'm also going to assume that on the other side, the co-kernel is going to be one-dimensional. This assumption is natural because I want to have as many equations as variables. Otherwise, I will clearly have no chance to apply the implicit function theorem in a good way. Okay? So that's somehow a natural assumption. Making this here and phrasing this in terms of the index would be just saying the index of this Fredholm operator is 0. By the way, in the case of a self-adjoint operator and a discrete eigenvalue, this will come for free. Okay, as Fritz had on his slides, the co-range will be just the orthogonal complement of the range. This will be the kernel of the adjoint. If the operator is self-adjoint, you get the same dimension as before. So this will be true in our situation. But as I said, it's important to have as many equations as we have unknowns, because otherwise things are not going to work out. Okay, so in our sense, this is satisfied, and this will come more or less for free from self-adjointness. Okay, so making this assumption, what does it mean? It means here this U, it's a one-dimensional space, so let's choose some vector U0 which spans the kernel, and then just write U as lambda times this basis vector. Natural thing. And same thing on the other hand, this will be a multiple of a vector u1 which spans x1, so this will be a multiple of this vector right here. Once we have chosen our basis, this is precisely what we're doing here, we really have a function which goes from R2 to R. Okay? And this is this function f, which I call right here. Of course, nothing special here has been going on. We still have a nice C1 function. We still have our trivial solution. And we still have our bifurcation condition that the derivative with respect to lambda of this function is equal to 0. Okay, so far so good. We know we have this trivial solution. So that suggests itself to write this function f as lambda times another function g. So we kind of split off the thing we already know. That of course works. Again, you use the L'Hopital to show that the derivative here 1 over lambda is fine. So under the C1 assumption, you can write this as lambda times a function which is continuous at this point. It will be C1 on the rest, but of course at this point, because of pulling this piece out, you lose differentiability. Okay? This function g here will no longer be C1 if f is just C1. Okay? But we would like to apply the implicit function theorem. We would like to apply to take another derivative. So let's just assume that everything we have started with is C2. Okay? Lambda is real. Yeah, everything. This is as simple as it can. Omega is real, lambda is real, f is real valued. Okay, we are really talking about first semester analysis here. The lambda was chosen here. It was my parametrization, my coordinates, right? This space U, this U which is in the kernel of A is a one-dimensional space, and I'm just writing it at lambda times this fixed basis vector U0. So it's just my coordinates such that it is really from R to R and not from an abstract one-dimensional vector space to another abstract one-dimensional. I want everything real valued. Okay, because otherwise I have complex differentiation. And even though I would have a complex vector space, I will just regard it as a real vector space, at least when I take my differentiation. Okay? So of course the space could be, I could take C2, but I take C2 and regard it as a real vector space. Okay, so we write it like this. We know from our bifurcation condition, this is the condition we have started with, that g at 0, of course you just differentiate this with respect to lambda, evaluate at 0, you see that these two pieces are equal. We know this one is 0. This is we derived along the way. So this is our condition that something could go on here. Okay, g vanishes at this point. Does it also vanish in the neighborhood? So do you get additional non-trivial solutions? Well, in order to do this, we're going to use the implicit function theorem applied to g. Okay? And as I said, we need C2. So let's just go back to the very beginning, assume C2, but everything I have done, if my function is CR, then everything in the end will also give me CR functions. Okay. So I want to solve implicitly for omega. So I'm assuming that at this point omega 0, this derivative here does not vanish. This is a number. Okay, we're talking about real numbers here. And if this does not vanish, the implicit function theorem tells me that I can solve this equation, and hence I get another solution. This is the trivial one, plus the solution of this function g. So really something new comes up and something new is happening right here. And the condition, of course, is differentiating g with respect to omega, and if you use this definition here, you will see that this is the same as first differentiating with respect to lambda, such that the lambda goes away, evaluating at 0, and then differentiating with respect to omega. So this is the condition here. This must be non-zero. Then I can apply the implicit function theorem, and it will give me existence of a non-trivial solution. Okay, now what we need to do back, I'm a bit sure here you need to work a little bit, so it's a lengthy calculation, but now you just need to trace back. Okay? The question is, what does this final condition we got here mean in terms of the function we have started with? But this is really just tracing back everything, computing these derivatives in terms of what we had before. And it's not very surprising. This is the one we need. You will see later why I also work out the other one. In the end, it's just differentiating your function we have started with respect to omega and with respect to x, evaluating everything at this bifurcation point omega 0 and also at the point x is equal to 0. And of course, because of the chain rule, you also get this vector back right here. And since it's just the first component, you still have this projection q, but since it's linear, you can put it inside, you can put it outside just as you want. And also because you will see this now in the formulation of the theorem, we had that this derivative here should be non-zero. This is the condition we got out of this. This is the condition we need. What does it mean in terms of this thing here? This should be non-zero. What does it mean? It means you take this derivative here and then projecting, it should be non-zero. This is the projection onto what is not seen by the range. So that means that this must have a component which is not in the range of the operator. Okay, this is really what it says, because then once you project, you get only this component, and this component must be non-zero, because this is what we're going to formulate in the using in the formulation of this theorem right here. So summarizing, what we have done is the following. We take some function f, which is C2, depending on some parameter in R, and living in some Banach space X, such that we have a trivial solution. We're assuming that we have found some parameter omega naught, such that the derivative at this parameter and that the trivial solution is a nice Fredholm operator of index 0 with a one-dimensional kernel. Okay? This kernel is spanned by this vector u0 here, and if the second derivative here applied to u0 gives you a vector which is not in the range of your first derivative right here, I just explained where the range condition is coming from, then you have a nice neighborhood, and in addition to the non-trivial to the trivial solution, you get a trivial solution. And you can even write down some explicit formula for them. So this solution then is given by this expression here if you trace everything back, and you can even write down a local approximation to this solution. This is why I have computed these derivatives just before. So it starts off from the parameter omega 0, of course. Then you have this linear term in terms of this parameter lambda right here with an explicit given derivative plus some smaller order terms. And also the solution looks like lambda times this eigenvalue plus some smaller order terms. So you see that works very nicely, and this is what you get out of just applying some abstract nonsense. Yeah. I'm afraid I cannot answer your question. I presume maybe 50s, maybe a little bit earlier. I also don't know what they really had in mind with these things, but it's clear, and it's also one of the reasons why I have presented this. There are a couple of examples to which you can apply this. So there are many, but it's clear if you look at the formulation. There are many things which you can just look at as finding the zero of a function in an abstract space, and you differentiate, you have a linearization, you look for the eigenvalues, and you try to verify this condition here, and you can ensure existence. What is the geometric picture one should have here? That could well be, but I'm afraid I also cannot answer this question. So No, here you have to be a little bit careful. The theorem does not tell you what kind of bifurcation we have here, okay? Because the situation looks like this, right? We have omega in this direction. This is this point omega 0 where something goes on. And then let's just plot lambda here in some sense, taking lambda as the parameter, which maybe lambda is not good, but it's that would be x, so that would be the non-trivial solution. So this is x is equal to 0, which is the trivial solution, and this of course is an infinite dimensional space, which I just draw as a one-dimensional one. And of course there are different things what could happen here. It could be that you split up into two solutions and you have something like this. Okay, that should be a parabola. I'm not very good at drawing, but this is something what, for example, could happen, what people would call a pitchfork perturbation, bifurcation. Could also go to the other way, and it could also look something like this. In omega 0 here, there could be a crossing. Okay, so this non-trivial solution could just cross the trivial one at this point. So there are different things which could go on here, and of course you would need to investigate the higher order derivatives. So if you look at the formulation here, so for example, if this second derivative here vanishes, then that's very much an indication things vanish here, so that you're in such a situation that you have a parabola. Of course, you would still need to check the next derivative and make sure that it does not vanish, that you really have a parabola right here. If this does not vanish, then you clearly have such a crossing point. Okay, so you could further classify this, but for the moment we are just happy that we have found something, and you could investigate it further, what kind of bifurcation you have here. But as I said, we want to have a solution, so we don't care much about the precise details of the bifurcation going on here. Okay, so that means we have established some non-trivial solution of our, well, we have not established this yet. Of course, we need to go back to our stationary discrete nonlinear Schrödinger equation, and we need to apply this. Okay, I have raised my condition here such that this function here is C2, and we have seen, okay, this is our operator. We need a non-trivial kernel, which means we need an eigenvalue for this operator here. We need to check these Fredholm conditions, but I told you in order to have the range closed, you will need a discrete eigenvalue. Okay, so you need to be away from the essential spectrum to ensure this. So you need a discrete eigenvalue, but once you have a discrete eigenvalue, you get the fact that your index is 0 for free from self-adjointness. Okay, this is true. Now, what about simplicity of the eigenvalue? Well, in a higher dimensional situation, typically the lowest eigenvalue, the ground state, would be simple. Here in the one-dimensional case, it's actually true that such a one-dimensional Schrödinger operator, doesn't matter if it's discrete or continuous, always has only at most one eigenfunction. Okay, so spectrum, the point spectrum is always simple, so also this is satisfied here. In the discrete case, the easiest way to see this is remember the Wronski determinant I had on one of my slides before, and remember that I told you that the Wronski determinant of two solutions is 0. Okay? Now look at the Wronski determinant of two eigenfunctions. Both of them are square summable. So if I evaluate the Wronski determinant, which is constant, so I can pick any lattice point to evaluate, let's the lattice point go to infinity, everything goes to 0, so the Wronskian is 0, and this tells us it's one and the same solution up to a constant, so we have a simple eigenvalue in this situation. Right here. So far so good, so we need to, only it remains to check this final condition right here. Well, it's not hard to differentiate this with respect to omega. We just get minus the identity here. So that means this is equal to is equal to minus u0, and that should not be in the range. But we have a self-adjoint operator. The range is just the orthogonal complement of the adjoint, which we can forget about because it's a self-adjoint operator. Well, but this is in the kernel, so it's definitely not going to be in the orthogonal complement of the kernel. So also this condition is satisfied, and our Grandal-Rabinowitz theorem tells us that we have existence of a stationary solution in a neighborhood of this eigenvalue omega 0, and we could further go on investigating this situation. And maybe also still let me add something to the question you have asked. I should also emphasize that this is only one possible result here, right? Of course, there are many other possible situations you can think of how something could bifurcate. So in the end, it really boils down to making a Lyapunov type Schmidt reduction. So you need to assume that at your bifurcation point you have a Fredholm operator. Then you can make this Lyapunov Schmidt reduction. You reduce it to a finite dimensional point, and then it just remains a finite dimensional problem. It just remains to investigate this finite dimensional problem. Okay, and this is, if you look into an ODE book, you will find all kind of classifications of finite dimensional bifurcation points for finite dimensional ODEs. All that immediately applies here. Okay, and in some sense, the Fredholm condition is what makes it work, because you have this nice block structure and the fact that implicit function theorem and so on all exists nicely in the infinite dimensional setting. So this is just the tip of the iceberg. This is just one nice example showing you how to apply things, but it's clear you can go further, you can derive more results, and of course there's a large amount of literature on this subject. So what else can you do? I'm afraid I don't have enough time to say much more, but the next step is then, well, you have this solution, you ask yourself, is the solution stable? So if you perturb the initial condition a little bit about this solution, do you stay there, yes or not? So this is this stability problem, and this can also be investigated, and here again the dispersive estimates, Strichert's estimates, are going to be the crucial ingredients. There are here not. In the continuous case, yes. Okay, in the discrete case, you don't need it, but here you also need it in the discrete case. For the stability, precisely. Okay, so what you're doing is, okay, you look at your solution, you assume it starts close to this one, and then it doesn't really stay close. The question is, how do you formulate stability? You need to formulate it in such a way that you allow these parameters here to be t-dependent. So they could change. You kind of look at this manifold which is spanned by the solutions, and you allow the parameters to move on this manifold, and then you stay close to this manifold. So this is the correct formulation in this context. And so you make this ansatz here for the solution. You say it looks like the stationary, up to the fact that the parameters here in the stationary solution are now t-dependent plus a small perturbation. And you assume that initially this small perturbation is sufficiently small. Then you split these differential equations into real and imaginary parts so that everything is real valued again, and then you just apply this estimate and prove that the corresponding system for Z really is asymptotically stable, and hence you get stability of these results right here. So for this particular case here, it was in the paper, that was done in this paper I have listed here, but of course this is really a long story. It has been done for many equation, continuous, nonlinear Schrödinger equation, one-dimensional, multi-dimensional. So this is a vast subject, and there are of course many physically interesting equations, and people looked at most of them so far, and there are still equations are showing up all the time, so there's a lot of things you can do if you want. Pick one of these new equations and try to apply it and see how far you get. Okay, so this is all I wanted to say, so thanks for your attention. Yeah, I mean, definitely it's what one would expect, but I haven't looked at this literature recently, so maybe that has been done. Maybe it's still open, and that would be an interesting problem to look at. But The subject here is really very vast, and it's growing very fast. So new papers are always appearing, and it's almost impossible to be up to date what has happened. So you really need to go to Mathscinet and check and see if there is anything available. So when I last looked at this, but it's already maybe 1 or 2 years ago, I think it's maybe 1 year ago, I haven't seen anything in this direction. But maybe that's no longer true, or maybe I also missed something. I did not really search carefully. Yeah, so let me thank again for the invitation, and let's also give a hand to the organizers. But maybe we should do this tomorrow, but I'm still saying it yet because I won't be here tomorrow.